Okay, so let's get started. Now, last time I spoke about the homotopy axiom, but I didn't prove it. So today I want to give a proof, and you will be glad that you are attending class today, okay? Because there's a proof in the book, Differential Forms in Algebraic Topology, and I have another proof in the book on manifolds. But last year, I realized that there's a simpler proof, much simpler proof. And so that's what I'll present to you today, okay? And the other proofs, when I look at them now, they're horrible. Uh, however, because this simpler proof has not been published, you better watch me like a hawk, okay? Make sure that I'm not making any mistakes. Yeah. All right. So today is lecture 6, and we will talk about a proof of the homotopy axiom. And I also have time to talk about the Mayer-Vittora sequence for compact support. All right, so let's start with the homotopy axiom. Okay, now we all know that a C infinity map of manifolds pulls back differential forms Mhm. And this pullback map commutes with the exterior derivative. So it's a co-chain map, and the co-chain map induces a map in cohomology. And that map I write as F hatch. But we often also write this as F star. Okay? And the homotopy axiom says that two homotopic maps induce the same map in cohomology. So if F0 is homotopic to F1 from N to M, then the induced maps F0 hatch and F1 hatch are equal. Okay, yeah. All right. Uh, uh, so the proof starts with the reduction to a special case. Reduction to two inclusions. Now, to say that they are homotopic, means that there's a map F so that at time 0, it's F0, and at time 1, it's F1. And this is, yeah, so this is N, all right? Yeah, and this is N. And this is the interval 0, 1. Okay, so, yeah, so here it's N cross 0, 1. And yeah, so I'm gonna define the inclusion map JT from M to from M cross 0, 1, from M into M cross 0, 1, where JT of X is just XT. Okay. Mm-hmm. Yeah. Okay. Now, so if you define this, then so here I have a homotopy, and that means F at time 0 is F0, and F at time 1 is F1. Okay. So I can write F0 of X is F of X0, and that's F of J0 of X. J0 of X is X0. Mm-hmm. And then F1 is also a composition. So F1 of X is F of X1. That's F of J1 of X. So F composed with J1 of X. Huh? Yeah. Okay, now you know that the pullback has this functorial property, that the pullback of the composition is the composition of the pullback. So by functoriality, F1 hatch, so let's start with F0. F0 hatch is F composed with J0 hatch, and that's J0 hatch composed with F hatch. Okay. And F1 hatch is going to be J1 hatch composed with F hatch. So to prove that these two maps are equal, it's sufficient to prove that J0 hatch and J1 hatch are equal. Okay? So now I have reduced the problem from two arbitrary maps to just two inclusions. Yeah, so that's a big improvement. Now you only have to look at these two very specific and simple maps. And in algebraic topology, okay, to prove that two maps in cohomology are equal, there's a standard method. And it's called the method of co-chain homotopy. Okay? It's a very general method, works all the time. If you can find this co-chain homotopy. So let me explain the method. Okay? I mean, it's good to know this method. So what is the co-chain homotopy? So suppose you have two co-chain maps of differential complexes. Let, say, phi and psi going from one co-chain complex to the other be co-chain maps of co-chain complexes. Well, what does that mean? Well, A is a co-chain complex. That means you have a sequence of linear maps with a differential d, so the d squared is 0. So this is A, okay? And B is another co-chain complex. Okay, and we call its differential also D. And a co-chain map from A to B, it's a sequence of maps, one for each K, you know, from A to B. So this would be a co-chain map, phi. And it commutes with D. Okay? The diagram is commutative. Okay? And a co-chain homotopy, it is a linear map that decreases the degree by 1. So a co-chain homotopy goes this way. Okay. One for each K. Okay. Co-chain homotopy from, say, phi to psi is a collection of linear maps K from AK to BK minus 1 one for each K, such that if you go this way plus this way, it's going to be equal to this, the difference of the two cochain maps, okay? So such that dk plus kd is equal to psi minus phi. Okay, that's a cochain map. And dk, because k decreases the degree by 1, and d increases the degree by 1, so dk will preserve the degree. So it's going to go from ak to bk. Yeah. Okay, so that's a cochain homotopy. And the important thing is that a cochain homotopy, if there is a cochain homotopy from phi to psi, then phi and psi induce the same map in cohomology. Okay? Yeah. So let's write that down. So that's a theorem. If there exists a cochain homotopy K from phi to psi, then the induced maps in cohomology are equal. Okay, so let's prove this. The proof is very simple. Yeah, that the class of A be a cohomology class of the cochain complex A, and then we look at phi hatch of A, and by definition, it is the class of phi of A. Okay, but we have a cochain homotopy, and it's down here. So phi of A and psi of A differ by this. No, maybe I should start with psi here. Psi. Yeah, so psi of A is going to be equal to dk A plus kdA plus phi of A. Okay? Because you have a cochain homotopy between the two maps. And then you see that, well, because A defines a cohomology class, dA is 0. That term is 0. But the cohomology class of an exact form is 0. Okay, so you have this, and this is 0. the class of an exact form. And so you see that, and this is phi hatch of the class of A. So you see that the two maps are equal in cohomology, okay? Okay. Yeah, so now we want to prove this. And what we have to do is to find a co-chain homotopy between the induced maps on forms. Oh, yeah, right, good. Thank you for asking. Okay, so this term is zero because to define a cohomology class, dA has to be zero. Right. By definition, the cohomology class, cohomology is co-cycles over co-boundaries. And so to have a cohomology class, you have to begin with a co-cycle, and that means dA is zero. Okay? And this term is zero because cohomology of A is defined to be the co-cycles over the co-boundaries. And the co-boundaries are all those that are of the form D of something, right? So it's A. The co-boundaries are, so yeah, say, you know, yeah. I don't want to use B, so maybe I say A prime. So A prime in A. Right. So if you have D of something, then its cohomology class is zero. Okay? Yeah. Yeah. Okay, good. Well, whenever you have a question, I really appreciate it if you ask the question. Okay. Yeah. So we know that, yeah, so F0 from N to M induces, F0 star on forms by pullback. These forms, they form a differential complex with the exterior derivative D. And because F star commutes with D, it's a co-chain map. And the same with F1. So you've got two co-chain maps, and you want to show that the induced maps in cohomology are equal. And all we need to do is to find a co-chain map, a co-chain homotopy. Okay? And if I remember correctly, there is actually a theorem that says that if two co-chain maps induce the same map in cohomology, then there exists a co-chain homotopy between them. Okay? The problem is to find it. You know it exists, but you have to find it. So we need a co-chain homotopy K we need a co-chain homotopy. Oh, yeah, a co-chain homotopy K from J0 star to J1 star, right? Because we reduce the problem to just these two inclusions. And let's see. All right. Now, so J0 goes from M to M cross 0, 1. And so J0 star, it goes from the forms on M cross 0, 1 to the forms on M. And so, so K, it has to go from this is your A, this is your B. It has to go from A in degree K to B in degree K minus 1. Okay. There is a natural map that goes from a form on this to a form here that decreases the degree by 1. And what is it? Well, you see, what you have here is a product of M with the unit interval. And you have a K form here. You want a K minus 1 form here. So the natural thing is to integrate along the fiber. So the fiber is the inverse image of a point. If you integrate, let's say this interval has coordinate t. So if you integrate with respect to t, you are going to get rid of t, get rid of dt, and you will reduce the degree by 1, okay? Yeah, so let's define integration along the fiber. We first do it for a chart, because on a chart, you have coordinates. So let's say this is U, and then the coordinates are x1 to xn. And then on the unit interval, the coordinate is t. Okay? And let's define integration along the fiber. on U cross I. U has coordinates. Okay. So a K form on U cross 0, 1, well, it has to be a linear combination of wedges of forms, you know, dt and dxi, right? So it either has dt in it or it doesn't. So a form on this product is a sum of two types of forms. Either it has dt or it doesn't. So type 1 would be f of xt dxi1 which dxik. Or it has dt in it. So it could be g of xt dt wedge dxi1 wedge let's call it j1 now, dxjk minus 1. Okay? And then define k from k forms on U cross 0, 1 to k minus 1 forms on U by integrating with respect to t. Okay? Yeah. Move this down. All right. So on type 1 forms, okay, you have k of, well, let's introduce a shorthand. So this I will just write as f dxi. And then this type 2 form I will write as g dxj. Okay? So k of f of xt dxi should be, what should it be? What should it be? I'm integrating with respect to t. 0, right? Because there's no t there for you to integrate. And then on type 2 forms, it should be, well, you just integrate with respect to t from 0 to 1, and then you have your dxj left, okay? And it will have degree 1 less. And now you have to check that dk minus plus kd is equal to j0 star minus j1 star. Okay? If that's true, then you have a co-chain homotopy, and then you know that these two maps will induce the same map in cohomology. Okay, so we checked it on the two types of forms. On type 1 form, so you have dk plus kd applied to f xt dxi, and k applied to the type 1 form is 0. So it's just kd Okay, now let me give you a quiz right now. What is the exterior derivative of f dxi? Can somebody volunteer? It doesn't matter if you get it wrong because, it's only me that's being filmed. Nobody knows who you are. How do we take the exterior derivative of a function times dxi? Oh, good. Yeah, partial with respect to, say, xj, right? And then dxj, right? That's df, wedge dxi. And you sum over j, but there are several variables here. So there is another term, right? What is the other term? I mean, you have to take df. Huh? So can somebody tell me what the other term is? You see, the definition of d is that it's k of df, wedge dxi. Okay? And so df is this plus yeah, right. You have to take the partial with respect to all the variables. So there is a df dt wedge dxi. Okay? Right. Okay. Okay. Now, what is k applied to this sum? 0, right? Because this is type 1. So k applied to this sum is 0 because it's type 1. K applied to this is the integral with respect to t, wedge with dxi. So let me do it over here. So I get the integral df dt from 0 to 1 dxi. Okay. And this, by the fundamental theorem of calculus, is f evaluated from 0 to 1. Okay. So that's what it is on the left-hand side. And then on the right-hand side, I have to do J0 star minus J1 star apply to f of xt dxi. All right? And so this is going to be, J0 star of f xt, okay, d J0 star of xi, because star commutes with d minus J1 star fxt d J1 star xi. Okay? Okay. And okay, and J0 star of no, what is it? F. J0 star of f of xt. Um, J0, well, when you pull back a function, well, let's just do this. Okay, we have to figure out what this is. Okay? J0 star of f. Now, J0, it's the inclusion into the product. So when you pull it back, it's just a function on U. And the pullback is the composition. So it's f of J0 or x is x0. Okay? All right, so that's what it is. Okay, and then what is J0 star? Oh gosh, I guess it's a very bad notation, right? Well, yeah, yeah. I mean, let's leave this, okay, as J0 star of dxi and J1 star of, no, just a minute. I think, okay, I think I actually want J1 minus J0. I'm going from 0 to 1. So this should be 1, 0, 1, 1, 0, 0. Okay? Yeah, so J0 star dxi is J0 star dxi1 to dxik. And the pullback commutes with the wedge and with D. So I get D J0 star xi1 wedge D J0 star xik. Okay? And so I have to know what the pullback of xi is. So the pullback of xi, that should be a function on U. So let's see what it is from A1 to AN. And it's going to be the composition, xi, composed with J0, A1 to AN. And so it's xi. Now J0 maps this point in U to the product, right, whose time coordinate is 0. Xi means you take out the ith component, so it is AI. And AI is xi applied to A1 to AN. If you compare both sides, you see that J0 star of xi is just xi. Thus, so J0 star of dxi, it's just dxi. Okay? And now, let's look at what we have to calculate. So, yeah. So J0 star F, J0 star dxi. It's just, this is J0 star of xt. Looks like I have erased it, but I remember that it's just x0, f of x0, and then dxi. Okay? And so the right-hand side of the co-chain homotopy equation is going to be f x1 dxi minus f x0 dxi. And then, yeah, it's here. It's the same as the left-hand side of dk plus kd is equal to J1 star minus J0 star. Okay? So that proves that we have a co-chain homotopy, okay, on a chart. Now we have to extend it to a co-chain homotopy on M. And basically, what we have to do is to define integration along the fiber on M. Oh, right, we did only part one. Right, type 1 forms. Good point. Okay, yeah, but for type 2 forms, you know, the calculation is very similar. So I will just say that it's similar, and I won't do it on the blackboard. I'm going to post this new proof on the internet and on the Cool Course site. So if you can't do it yourself, you can just look at this posting. So on type 2 forms, yeah, computation is similar, right? All right, so Let's take a break, until 11:23, and we'll continue after that. Okay, so let's get started again. Um, Now, one student just pointed out to me that what I have done on the board so far is exactly the same as the proof in the book, An Introduction to Manifolds. Uh, I'm so glad that you have been reading the book. And yeah, but the next step is different. Now we want to extend integration along the fiber from a chart to a manifold. And uh, the way it's done in the book is very complicated. And now I have a simple way. Okay. All right. So this is where you have to watch me carefully. Okay? Um, I'm going to, okay, so integration along the fiber on a chart that we have defined is in terms of the coordinates x1 to xn. And I want to prove this proposition that it is independent of the coordinates. So if I have another set of coordinates, y1 to yn, on the chart, then integration along the fiber defined using y is the same as what you get defined using x. Okay, so let's see. How should I state the proposition? Um, so let u x1 to xn and u y1 to yn be two charts on the same open sets. So the definition of K, which is integration along the fiber, from forms on U cross 01 to forms on U is independent of the coordinates. So it's the same. Yeah, so gives the same result. In either coordinate system. Okay. All right. So we start with the form on the Cartesian product. And it can be written using the x-coordinate system. Oh, so yeah, so let's look at type 1 forms first, okay? So if it's a type 1 form, then in the x-coordinate system, it has no dt, and in the y-coordinate system, it has no dt either. Well, you see, if it has no dt in one coordinate system, it has no dt in the other coordinate system, because there's a formula that transforms dxi to dxj to dyi, right? And that doesn't involve any dt's, okay? So we have this formula, dyi1 wedge dyik. Okay. Now in the x-coordinate system, it would be a linear combination of the xj1 wedge the xjk. Okay. And does anybody know what the coefficients are? Yes, yeah, it's a Jacobian determinant, okay, of the y's. So it would be dy alpha with respect to the xj beta. Okay. Where alpha and beta go between 1 and k. Okay. So we have this formula, and it's in my manifold book. And let's just simplify the notation a little bit by writing this determinant as dyi over dxj, okay? So that's just notation. Yeah, so we can write it this way. Yeah, so you see, yeah, if you replace the y, just a minute, this should be I, right? Yeah. Yeah, you can replace dyi with the xj, and there wouldn't be a dt in it. Yeah, yeah. So a type 1 form is a type 1 form in any coordinate system. Is that okay? Okay, yeah. And now, okay, and now let's look at the definition of integration along the fiber in the two coordinate system. Yeah, so in the x coordinate system, so k of f, well, let's just say k of omega is going to be the sum of the integral. No, it is just 0, right? Yeah. Oh, yeah. So in the x coordinate system, you get 0. And in the y coordinate system, you also get 0. Because it's also a type 1 form. Okay, yeah, so that's fine. Now let's check type 2 forms. For a type 2 omega, so it is going to be Okay, so let's say it is f of xt dt wedge dxj, okay? And then in the, oh, and this should be x f sub j, right? Oh, yeah, right. I don't know. I should put j here. Oh, no, this should be a different function. It's a gi. The coefficients with respect to the y should be different from the coefficients with respect to the j. Yeah. And so for a type 2, I have omega is the sum of gi yt dt wedge dxi, dyi. And so now let's check in the x-coordinate system, k omega is the sum of the integral from 0 to 1 of fj xt dt times dxj. Yeah. And then in the y-coordinate system, I have a different formula. K omega is the sum of the integral of gi yt dt times dyi. Okay? But I know how dyi is related to dxj. So dyi is the determinant dyi dxj dxj. Yeah. This is sum over, now this is sum over I and j. Okay. And now because this determinant does not depend on t, I can bring it inside the integral. Okay. Okay. And the index j. Oh, so j is all j1 to jk. It's all possible j1 to jk. Hmm? Oh, right. Yeah, k minus 1. That's right. Yeah. Thank you. Yeah. And I goes from I1 to k minus 1, right? Because there's a dt there, so I also has only k minus 1 superscripts. Okay? Yeah, right. So anyway, so yeah, this is a square matrix, and you can take its determinant. Okay, okay, thank you. Yeah, so we want to compare this formula with this formula. Okay? But let's see, how are F and G related? So let's go back here. Yeah, so over here, so this is GI dyi running out of space. Let me see. So this is GI dyi is dyi over dxj, dxj. And now I sum over ij, right? So I have this formula that fj is equal to the sum of this over I, okay? So is there a, yeah. Oh, sorry, yeah. We should go to type 2, right? Where's type 2? Yeah. Okay, yeah, it's over here. Good. I want to relate the coefficients. Okay. Let me see. So what should I keep? Yeah, let's start over here. Right. Okay, type 2 is down there, and I want to relate the coefficients in the two-coordinate system. Okay. Yeah. So omega is the sum of fi dt, fj dt wedge dxj, and it's also gi dt wedge dyi, and I'm going to replace dyi by the determinant times dxj. So this is sum over I and then sum over j, right? Okay, no, so let's do sum over j and sum over I. Okay? So if you compare the two sides of the equation, thus fj is the sum over I of gi dyi dxj. Okay, so that's how the coefficients are related. And now we're calculating K of a type 2 form, and we got this. Yeah. We got this. And now, of course, I can first sum over J, then sum over I. And integration commutes with the sum, so I can bring the sum inside. And you see that sum there is precisely Fj. So, yeah. Okay, so this is the sum over J of the integral from 0 to 1 of Fj xt dxj. Yeah, so you see that in the y-coordinate system, the answer you get is the same as the answer from the x-coordinate system. And that proves that integration along the fiber is independent of the coordinates. Okay? And so now you can extend it to an entire manifold. Okay? Um, first of all, you cover, M with an atlas. And then you let omega, be a form on M cross 0, 1. And on each chart, and then let's say the restriction to U alpha, we call omega alpha. Okay, so on each chart, we have defined K of omega alpha. Oh, yeah. U alpha cross 0, 1. Yeah, thank you very much. What is your name? Su Ping Chen. Okay, good. And then, well, and then on the intersection, on U alpha cross 0, 1, intersect, say, U beta cross 0, 1, which is the same as U alpha intersect U beta cross 0, 1. We have two coordinate systems, but we know that they agree. K omega alpha is equal to K omega beta. So therefore, but this is, yeah, once you have defined this, it is downstairs, right? So it's omega K of U alpha. Yeah, but you start here, and then they agree, and they're downstairs, and it's degree 1 less. So therefore, they piece together to form a global form. To give a global form K omega. And you will still have the Chen homotopy equation because this equation is an equality of forms. And to check the two forms are equal, you only have to check the two sides locally. So this is an equality of forms. And hence can be checked locally. And we already know that it's true locally. And so we checked it locally already. Eh? So it's true on M, and therefore you have a cochain homotopy on M. And so that gives you the homotopy axiom. Okay. All right. So we'll stop here today. I was going to go talk about the Maya-Vittora sequence for compact support, but we don't have time. We'll do that next time. All right. Okay. So.